Backpropagation. What does it do? Backpropagation computes another set of functions for every computed neuron, for every neuron except for those in the input layer. And first, I will introduce the notation for those functions. I'm going to call them delta, jk. These are vector functions of several variables. And again, k here represents the layer index, and j represents the index within the layer. Mathematically, those functions are simply the following partial derivatives. These are the partial derivatives of your network function. Now, backpropagation gives you the recursive relation, which allows you to compute every such function. Let's just see how it works. You start by computing this at the output layer. That's where it takes the simplest form, because at the output layer, if your k is p, at the output layer, your f is the b function of the output layer. So if you attempt to find the delta function at the output layer, this is what happens. All you do, you differentiate the b function at the output layer with respect to the a function again at the output layer, and these two are connected directly through sigmoid. So all you end up having is just the m tuple of derivatives of the sigmoid at the a functions at p level. And that's how you compute the initial value of your delta at the output layer. Now, delta functions at the other layer, they require a recursive relation. The relation itself looks like this. The delta at the layer to the left connected to the deltas at the layer to the right, again through weights and derivative of the sigmoid at the layer to the left. If you're only interested in implementing backpropagation, these two formulae all you need to know. These two formulae all you need to know. And you can actually fast forward to the next chapter in this discussion. However, if you would like to know more about why this is so, I will explain it in the next few minutes. Why does the backpropagation formula takes the following shape? The reason for that, it's an application of the known chain rule result. So in order to understand how the chain rule works in this result, we need to first trace the perturbations through the network. And that's where actually topology of the network plays a significant role. So what I'm trying to say is this: if you do a minor perturbation of the a function at the k take one layer, this perturbation will propagate through the network. And these two arrows, they try to explain how exactly that propagation will happen. Perturbation of the a value will result in a perturbation of the b value at the same level, and then through this relation, this perturbation will affect the a values, all of the a values in the layer to the right. If you keep this in mind, then we can try to see how the chain rule works for the backpropagation formula. Look at this. First, I will observe that the moment you try to find the derivative of f with respect to a value, the k take one layer, you can first use the chain rule from this relation. You can connect this to the derivative with respect to b, and that's what you end up having if you do so. This is very similar to this one, to the initial value of the delta functions at the output layer. But then, when you focus on this derivative, and you aim to link this to the derivative with respect to a's at the layer to the right, that's where the chain rule works the hardest, because that's where the chain rule works from this relation. And when you do this derivative, df by bk, you run the chain rule. This is a chain rule step. And these factors you have from the chain rule is exactly the weights from this relation in a forward propagation formula. These two formulae, especially the second one, it's a very heavy application of the chain rule. If you struggle to understand this, it's not going to affect your implementation of backpropagation. But if you'd like to know more, you need to take a course in several variable calculus with a good presentation of the chain rule.